Namaskar, this is Nayan and I welcome all of you to my YouTube channel. Students, in my previous video, I explained the solutions for SLET 2024 Physical Science paper where I tackled a total of 5 problems. Today, we will continue on this journey by solving another set of 5 problems. So, without further delay, let's get started. Problem number 6. This problem number 6 is asked from electricity topic, and according to this problem, which statement is not true in the following? That means we have to find out the false statement out of these 4 options. Option A: for a test charge placed at infinity, the electric field will be 0. This is true statement. Now let me explain you why option A is the true statement. Students, suppose we have a system of 2 charges. Plus capital Q is the primary source charge and plus small q naught is the test charge placed at a distance r from the primary source charge. If F is the force experienced by this test charge due to the primary source charge, then according to the definition, electric field at test charge q naught is defined as F divided by q naught. We know that the force experienced by the test charge due to the primary source charge is given by 1 by 4 pi epsilon naught q into q naught divided by r square, and the direction is along this direction. Now let us substitute this value here. So finally we will get electric field at q naught as 1 by 4 pi epsilon naught q naught divided by r square into r cap divided by q naught. So after simplifying, we will get electric field at the test charge q naught as 1 by 4 pi epsilon naught into q divided by r square into r cap. Now let us write down the magnitude of the electric field. The magnitude of the electric field at q naught will be 1 by 4 pi epsilon naught q divided by r square. Now when r equal to infinity, that means when we placed this test charge at infinity, then the magnitude of the electric field will become 0 because 1 by infinity is 0. So therefore this option A is true statement. Since we have to find out the false statement, so therefore option A is wrong answer. Now let us move to option B. According to option B, the Gaussian surface is tangential. This is false statement because we know that in general the Gaussian surface is spherical, cylindrical or planar in shape. Since option B is the false statement, so therefore option B is the correct answer. Now let me write this point. Gaussian surface is not tangential. It is in general spherical, cylindrical or planar in shape. Okay? Now let us move to option C. According to option C, Gauss law cannot be used to find permittivity. This is true statement because we know that with the help of Gauss law we can find out the electric field of charged objects having spherical, cylindrical or planar symmetry. It is not used to find out the permittivity. Now let me write these points. Gauss law is used to find electric field of charged objects having spherical, comma, cylindrical or planar symmetry. It is not used to find permittivity. Okay? Since option C is the true statement, so therefore this option C is incorrect. Next, move to option D. According to option D, charge in space is an example of spherical system. This is true statement. Since this is true statement, so therefore option D is also incorrect. Okay? So we have seen that option B is the correct answer to the question number 6. Okay? Next, problem number 7. This problem number 7 is asked from waveguide topic, and according to this problem, the modes of propagation supported by a rectangular waveguide is option A, transverse magnetic, transverse electromagnetic, transverse electric modes. Option B, transverse magnetic, transverse electric modes. Option C, transverse magnetic, transverse electromagnetic modes. Option D, transverse electric, transverse electromagnetic modes. Here the correct answer is option B, because we know that a rectangular waveguide supports transverse magnetic and transverse electric modes only. It does not support transverse electromagnetic mode, because in this case all field components vanish. First, let me write these points. A rectangular waveguide supports transverse electric and transverse magnetic modes only. It does not support transverse electromagnetic mode, because in this case all field components vanish. Okay? So the correct answer is option B. Next, let us solve problem number 8. This problem number 8 is asked from quantum mechanics topic, and according to this problem, in Fermi's golden rule, the transition rate is proportional to option A, the square of the matrix element of the perturbing potential. Option B, the inverse of the matrix element of the perturbing potential. Option C, the matrix element of the perturbing potential. Option D, independent of the matrix element of the perturbing potential. Here the correct answer is option A, because we know that according to Fermi's golden rule, the transition rate or transition probability per unit time associated with a transition from an initial state psi I into a continuum of final states psi f is given by this formula. Here h cross is the reduced Planck constant whose value is h by twice pi, and this term is known as the square of the matrix element of the perturbing potential, and this term is known as the density of states at energy EI. So here we have seen that this transition rate is directly proportional to the square of the matrix element of the perturbing potential. So therefore the correct answer is option A. Students, I have taken this definition from the book Quantum Mechanics written by Zetley. Okay? And this definition will be available at page number 579. Next, let me solve problem number 9. This problem number 9 is also asked from quantum mechanics topic, and according to this problem, the Hamiltonian of an electron in hydrogen atom is given by p square divided by twice m minus e square divided by r. First, let me write this point. So, given the Hamiltonian of the electron in hydrogen atom is P square divided by twice m minus E square divided by r. Again, this problem says that the wave function psi denotes the ground state wave function with this condition. That means, according to this problem, psi represents the ground state wave function. Ground state wave function. That means psi 1 0 0. So, where the principal quantum number is 1, orbital quantum number is 0 and magnetic quantum number is also 0. Also, this problem says that psi 1 0 0, psi 1 0 0 is 1. Okay? Next, we have to find out the correct answer out of these 4 options. Option A says that psi is an eigenstate of p square by twice m. This is not correct because we know that psi is a common eigenstate of Hamiltonian operator, L square operator and Lz operator only. Psi is not an eigenstate of kinetic energy operator alone. So, therefore, option A is not the correct answer. First, let me write these points. We know that psi n l m r comma theta comma phi is a common eigenstate of Hamiltonian operator, L square operator and Lz operator. It is not the eigenstate of kinetic energy operator alone. Okay? So, therefore, option A is incorrect. Now, let us move to option B. According to option B, the expectation value of R is 0. This is also not correct because we know that the expectation value of R is given by 1 by 2 into 3n square minus L into L plus 1 into A naught. Here, A naught is known as the Bohr radius. According to our problem, the principal quantum number n is 1 and orbital quantum number L is 0. So, after substituting these values here, we will get the expectation value of R as 3 by 2 into A naught, which is not equal to 0. So, therefore, option B is also incorrect. Next, let us move to option C. According to option C, the expectation value of 1 by R is infinite. This is also not correct because we know that the expectation value of 1 by R is 1 by n square into A naught. Here, A naught is the Bohr radius and n is the principal quantum number. So, according to our problem, the value of principal quantum number is 1. So, after substituting the value of principal quantum number here, we will get the expectation value of 1 by R as 1 by A naught, which is not infinite. So, option C is also incorrect. Finally, let us check option D. According to option D, the expectation value of Hamiltonian operator is less than 0. This is correct. Now, let me show you how expectation value of Hamiltonian operator is less than 0. Students, this term can be written as psi escape psi is equal to, we know that psi is psi 1 0 0. So, this term can be written as psi 1 0 0 escape psi 1 0 0. Again, we know that when the Hamiltonian operator acts on the wave function psi 1 0 0, then it will give energy E1 and the wave function itself. Here, E1 is the ground state energy of the hydrogen atom and it is a constant term. So this term can be written as psi 100 E1 psi 100. We know that E1 is a constant term. So therefore, this term can be written as E1 psi 100 psi 100. So according to our problem, this value is 1. So ultimately, we will get the expectation value of Hamiltonian operator as E1, which is the ground state energy of the hydrogen atom, and we know that the ground state energy of hydrogen atom is minus 13.6 electron volt, which is less than 0. So therefore, option D is the correct answer. Next, problem number 10. This problem number 10 is also asked from quantum mechanics topic, and according to this problem, the ground state energy of the electron in the hydrogen atom is option A 0.5 mega electron volt, option B minus 13.6 electron volt, option C minus 13.6 mega electron volt, option D minus 6.8 electron volt. Here the correct answer is option B. Now let me show you how option B is the correct answer. Students, we know that the energy of the electron in hydrogen atom is given by En is equal to minus 13.6 divided by n square electron volt. Here n is the principal quantum number which can take values from 1 to infinity. Okay? For ground state, n equal to 1. So therefore, the ground state energy of the electron in hydrogen atom will be E1 equal to minus 13.6 divided by 1 square electron volt, which is minus 13.6 electron volt. So option B is the correct answer. Okay? So this is all about today's video, and I hope that you have learned a lot from this video.